Good morning. This is Dr. K.R.K.V. Prasad, working as an associate professor in EEE department, Aditya College of Engineering and Technology. So I will deal basic electrical and electronics engineering subject for first years. See, before going to discuss about subject, first we will discuss content in each unit. In first unit, have DC circuits and AC circuits. In DC circuits, Ohm's law, KCL, KVL, series and parallel circuits we will discuss. And in AC circuits, definitions of different AC circuits and voltage current relationship with phasor diagram, concept of impedance and power factor. This part we will cover in AC circuits. And coming to second unit, here we will discuss about constructional details and working principle of all machines. Similarly, measuring instruments means PMMC and moving iron Wheatstone bridge. And coming to third unit, here we will discuss energy resources means conventional and non-conventional energy sources, electricity bill, equipment safety measures. So this part I will cover in third unit. So first we will discuss first unit. So here at the end of this course, a student can be able to understand the basics of electric circuits and understand working principles of all machines, and they can analyze different energy resources and equipment safety measures. So these are the course outcomes of basic electrical and electronics engineering. So first we will discuss basics of electromagnetic theory. So after that we will discuss about Ohm's law. See, coming to electromagnetic theory, so I will give brief introduction of electrostatics, magnetostatics and time varying magnetic fields. I will tell the differences. After that we will start Ohm's law. So this is the basic concept for all units. If you can understand the concept of electrostatics, magnetostatics and time varying fields clearly, then first, second and third units are nothing. They are very easy. See, first we will discuss electrostatics. So what is electrostatic? See, here electrostatics, magnetostatics and time varying magnetic field. See, first one I will split into three parts. First one, electrostatic. Second one, magnetostatics. Third one, time varying magnetic field. See, here simply I have taken a charge particle. See, if I take the charge, this is charge. This is charge. If I have charge, there exists electric field. See, always diverge the electric field from the charge. See, if it is positive charge, electric field is diverging. If it is negative charge, electric field is converge, means entering. See, these field lines are moving away from the charge. So, what is the field direction? It is radial direction. See, this is the field direction. Radially it is moving. Radially it is moving. So, if I have a charge, means this is stable charge. It is not moving. It is not moving. Here charge is not moving. So if I have a charge, there exists electric field. There exists electric field. So in electrostatics, charge is stable and there exists electric field. There exists electric field and it is not moving. Charge is not moving. Suppose coming to second case, take a conductor. This is conductor. This is conductor. And if I apply the electric field, what happened? That electric field applied on charge. That electric field applied on charge, that electric field applied on charge. See, without apply the electric field, what happen? If you apply the electric field, what happen? If you apply the electric field, the charge particles are moving uniformly with equal distance. Why it is moving with uniform velocity with equal distance? Why? What is the reason? Because here applied field is DC. Applied field is DC. Here applied field means uh, force on charge is constant. Means here charge particles are moving uniformly with equal distance, with maintenance of equal distance. So this is charge particle movement. But coming to time varying magnetic field, here which type of supply electric field we can apply? Here this one is AC. AC means here applied field is varying with respect to time, varying with respect to time. At t equals to 0, 0. At t equals to 1, some field. At t equals to 2, applied maximum. So it is varying with time. So that here charge particles are moving with acceleration and deceleration. Means positively increasing means this is acceleration, this is acceleration. After that it is decreasing, means force applied on charge is decreasing, force applied on charge is decreasing, field applied on charge is decreasing. That means charge particles are also varying in decelerating way, in decelerating way. Means here charge particles are decelerating, again charge particles are accelerating. Movement of charge particles is acceleration. Means from 0 to this part charge particles are acceleration, and this part charge particles are deceleration. This is acceleration, this one is deceleration, this one is deceleration. Okay, so and the distance between two charge particles are unequal. Why? Because applied field or charge particle is varying with respect to time, not is not maintained same. Here in case of magnetostatics, here time is constant, not constant. With respect to time, the applied field is always constant. At t equals to 0, same field. At t equals to 1, same field. At t equals to 2, same field. At t equals to 3, same field. Means applied field is constant. Applied field is constant. Clear? So here applied field is constant, so that if applied field is constant, the charge particles are uniformly moving with equal distance. Here applied charge is not constant, it is varying with respect to time. It is varying with respect to time. If it is varying with respect to time, the charge particles are also varying. If it is positively increasing, what is the charge particle? It is accelerating. It is accelerating. It is accelerating. If it is decreasing, charge particles are moving in deceleration mode. Means acceleration, deceleration, acceleration, deceleration. So if you apply AC, charge is moving with acceleration and deceleration. If you apply DC, charge is moving with uniform velocity and maintains equal distance between any two charge particles. But here distance is unequal. That is the major difference between DC and AC. When you apply DC and AC to the conductor, what happen? For DC, charge is moving with uniform velocity and maintain equal distance. But here charge is moving acceleration and deceleration with unequal distance. So here if charge is moving uniformly, due to charge is nothing but flow of electrons. Charge is nothing but electron. So here charge is moving means electrons are moving. See here flow of electrons flow of electrons are also uniform. Why? Because charge is moving uniform with uniform velocity. But here charge is moving with acceleration and deceleration. So that here electrons are also what is the velocity? Acceleration. Electron velocity is acceleration for positive. After that slowly decreasing means deceleration. So if electron velocity is acceleration and deceleration, flow of electrons is nothing but current. Flow of electrons is nothing but current. So that current is also here constant. Current is also varying means moving uniformly. Means current is constant. Current is constant. But here current is electrons are varying. Electron movement is varying acceleration and deceleration. So that current is also time varying. Current is also time varying. But here current is time invariant. It is not varying with respect to time. Okay. So here whenever the current passes through the conductor, see this is conductor. Suppose if the current passes through the conductor, what happen? Magnetic field is developed. What is that? Magnetic field is developed. Magnetic field is developed. Here also magnetic field is developed. Here also magnetic field is developed. Here also magnetic field. Here also magnetic field is developed. But which type of magnetic field? Magnetic field is directly proportional to current. Here current is constant, time invariant magnetic field. So that magnetic field developed in the conductor is also time invariant. Magnetic field developed in the conductor is also time invariant. So which type of magnetic field is developed? Constant magnetic field is developed. Constant magnetic field is developed. Here magnetic field is time varying. Time varying magnetic field. Time varying magnetic field. So here due to A, I am getting magnetic field H. Here also due to A, I am getting magnetic field H. So whenever the field applied on conductor, what happens? Charge particles are moving uniformly in magnetostatics. Here charge particles are moving in acceleration and deceleration in time varying magnetic field. Why? Because here applied field is time varying. Here applied field is constant. Clear? So whenever the constant magnetic field apply, here charge particles are moving with uniform velocity. Here charge particles are acceleration and deceleration. So that current is constant. Here current is time varying. Current is time varying. Due to constant current, which type of magnetic field is developed? Constant magnetic field is developed. Due to time varying current, which type of magnetic field is developed in AC, in the conductor? Time varying magnetic field. This one is time varying magnetic field. This one is constant magnetic field. But according to Faraday's law, if the conductor is stationary, if the conductor is means if one quantity is stationary, another quantity should be varying with respect to time or space. Then only you will get result. What Faraday said? If one quantity is stationary, another quantity should be varying with respect to either time or space. See, according to what Faraday's told? Faraday's law. So what he is telling? Faraday's law is nothing but time varying magnetic field. See, here if one quantity is stationary, if one quantity is stationary, another quantity should be varying with respect to time or varying with respect to space. Varying with respect to space. So, if one quantity is stationary, another quantity should be varying with respect to time or space. Suppose this is conductor, let us. This is conductor. Here conductor is stationary. Current passes through the conductor is time varying. Means conductor is stationary. Current passes through the conductor is varying with respect to time. Already I told you, sine wave. It is varying with respect to time. Current is varying with respect to time. Okay. Then only you will get some result. Suppose conductor is stationary, current passes through the conductor is also constant, will you get any result? No. Suppose, suppose, suppose magnetic field is stationary, magnetic field developed in the conductor is stationary, conductor is also stationary, no result. If magnetic field is varying with respect to space or with respect to time and conductor is stationary, then we will get the result. So from this, what you can give the conclusion? You have two terms. Either quantity is varying with respect to time or space or stationary. So if you can understand this principle clearly, you can enjoy second unit. Right. Anyway, here magnetic field is here magnetic field is stationary. Current is conductor is also stationary. It is not moving. Conductor is also stationary. It is not moving. So will you get any resultant? No. Why? Because both are stationary. Magnetic field is stationary. Conductor is also stationary. So we will not get any EMF in the conductor. But coming to third case, here conductor is stationary. Conductor is stationary. This is conductor. This one is stationary. But the magnetic field developed in the conductor is time varying. Magnetic field means magnetic field will rotate in clockwise or anti-clockwise, whatever. Here, let us magnetic field. This is the magnetic field direction. This one is varying with respect to time. This one is varying with respect to time. This is positive acceleration. This one is deceleration. Again, acceleration, deceleration, acceleration, deceleration. Means magnetic field is varying with respect to time, varying with respect to time, varying with respect to time. So, magnetic field developed in the conductor is varying with respect to time, but conductor is stationary. One quantity should be stationary. Here conductor is stationary. Another quantity, magnetic field developed in the conductor is varying with respect to time, with respect to time. So that again we will get the electric field, EMF. So that due to time varying magnetic field, again I will get EMF in the conductor. EMF in the conductor means electric field. Electric field means due to electric field, I am getting magnetic field. Due to time varying magnetic field, again I am getting electric field. Again I am getting electric field. Means here EM phenomena is exist. EM phenomena is existing. EM phenomena is existing. But coming to second case, here no EM phenomena. No EM phenomena. Why? 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 Because here due to electric field, I am getting magnetic field. But magnetic field is stationary. Conductor is also stationary. If both are stationary, will you get resultant EMF? Will you get EMF in the conductor? No. Already I told you. According to Faraday's law, if one quantity is stationary, another quantity should be varying with respect to time or space. But here, magnetic field is constant. Conductor is also stationary. So there is no EMF induced in the conductor. So vice versa is not possible. Due to electric field, I am getting magnetic field. But due to magnetic field, I will not get electric field. So that here EM phenomena will not exist. EM phenomena will not exist. Means here no EM phenomena. Sorry, this one is here EM phenomena will exist. EM phenomena will exist. So coming to first case, here there is no concept of magnetic field. So that no concept of EM phenomena. And here I will not give any supply. No supply. But here, which type of supply I am giving? Constant supply. Which type of supply I am giving? Constant supply. Here, which type of supply I am giving? Alternating supply. Alternating supply I am giving. Alternating supply I am giving. So, from this electromagnetostatics, what you can give the conclusion? According to Faraday's law, if one quantity is stationary, another quantity should be either varying with respect to space means sine wave, or with respect to with respect to time. Sine wave means with respect to time. Sine wave means it is varying with respect to time, like this, or it is varying with respect to space. With respect to space means this one is initially 0, 90, 180, 270, 360, like this, clockwise or sorry anti-clockwise or clockwise. That is varying with respect to space, quadrants. Clear? So final conclusion is, if one quantity is stationary, another quantity should be varying with respect to time or space. Then only Faraday's law will exist. So this is the conclusion of electrostatic, magnetostatic and time varying magnetic field. Next we will discuss about Ohm's law. What is Ohm's law? If you can understand electrostatic concept, Ohm's law is nothing. See, if you take a conductor, if you take a conductor and conductor see here, I will not apply any electric field. Here, suppose electrons are randomly moving. There is no electric field. Here there is no electric field. But if you apply electric field, all the electrons are moving in uniform direction, uniform way. These are moving in same direction. These are moving in same direction. These are moving in same direction. Why it is moving in same direction? Because of the electric field. Because of electric field. This is electric field. This is electric field. Because of electric field, all the electrons are moving in same direction. See, simple. This is classroom. Let us. This is classroom. Let us. So for that classroom, if there is no electric field means there is no faculty. If there is no faculty, all the students are playing in different way. All the students are moving in different direction. Will they move in same direction? Will they stay there in same direction? No, not at all. Similarly here also, if you will not apply any electric field, here electrons are nothing but students. So electrons are moving in random direction. But if you apply electric field, what happen? All electrons are moving in same direction. Same direction. So electric field means teacher. Here faculty is there. So that all the electrons are moving in same direction. See, from this, if you take this area, let us, if you take a small area, this is the area of the conductor, small area. So in that area, how much current passes through that area? Suppose only one means only one electron passes through the conductor, means current is less. Suppose if more number of electrons are passes, what happen? Current density is more. If less number of electrons means less amount of current passes through the conductor, current density is less. If more number of current passes through the same area, then current density is more. Current density is more. Simply just like tap. If you means open the tap, a small amount of water passes through tap, but valve is large. But tap, there exists only small amount of water. Then current density is small. But if full length of means current passes through the conductor, current density will increase. Means current density is nothing but current per unit area. Current per unit area. Current per unit area. Means in per unit area, how much of current passes through the conductor? How much of current passes through the conductor? That is current density. That is current density. That is current density. Clear? Means for the same density, for the same area, if more number of means current lines passes through that area, that then current density is more. If suppose less number, current density is less. Current density is less. So current density mainly depends on the amount of current passes through that area. The amount of current passes through that area. But here amount of current passes through that area depends on electric field. Depends on electric field. If you apply more electric field, more amount of current passes through the area. If you apply less electric field, less amount of current passes through the area. Clear? So here current passes through that area is directly proportional to electric field. Is directly proportional to electric field. Means E is nothing but V by L. Volts per meter. Volts per length. Clear? Clear? So from this, what is the relation? Current passes through the conductor is nothing but current passes through the small area is nothing but current density. But here the current density depending on current, but the amount of current passes through the area is depending on electric field. If you apply more electric field, more amount of current passes through the same area. If you apply less electric field, less amount of current passes through the area. So that current density is increasing or decreasing depends on applied electric field. Applied electric field means if you apply more electric field, then more amount of current passes through the area. So current density depending on J represents current density. J represents current density. Current density. I represents current passes through that area. A represents area of the conductor. A represents area of the conductor. Area of the conductor. But current passes through the area depending on applied electric field. Applied electric field. Applied electric field. If applied field is, if E is more, current passes through the area is also more. If current is more, current density is more. Vice versa. If E is decreasing, current is decreasing, current density also decreases. Current density also decreases. Current density also decreases. Means indirectly, here J is depending on I, but I is depending on A. So that indirectly, J is directly proportional to A. J is directly proportional to A. Current density is depending on applied electric field. So J equals to sigma A. Here J is current density, E is electric field intensity, and sigma is conductivity. Sigma is conductivity. Sigma is conductivity. Sigma is nothing but 1 by rho. Rho is nothing but resistivity. Rho is nothing but resistivity. Rho is nothing but resistivity. So J equals to 1 by rho into E. 1 by rho into E. So from this, J is nothing but, already we discussed, J is nothing but current per unit area, 1 by rho. E is nothing but V by L. So from this, V equals to rho L by A into I. Rho L by A is nothing but R, resistance R into I. So from this, V equals to IR, where R equals to rho L by A. So here V equals to IR is nothing but Ohm's law in circuit theory. Ohm's law in circuit theory. Here J equals to sigma is nothing but Ohm's law in field theory. Ohm's law in field theory. So if you ask the Ohm's law in examination, you have to write Ohm's law in electric field theory, and also you have to write Ohm's law in circuit theory. Ohm's law in circuit theory. Is it clear? So this is about Ohm's law. If you have any doubt, you can share your comment. And from this, finally, voltage, applied voltage is directly proportional to current. Means current is directly proportional to applied electric field. Current is directly proportional to applied electric field. So this is about Ohm's law. This is about Ohm's law. Next, limitations of Ohm's law. See, Ohm's law is applicable only for bilateral elements. Only for bilateral elements. See, see. Here, just remember this concept. Later we'll discuss. It is not applicable for unilateral elements. It is not applicable for unilateral elements. So after completion of the RLC components, resistance, inductance, capacitive components, and um, means after completion of RLC components concept, again we will come back to limitations. Just remember this point. It is applicable only for bilateral elements. Example, resistor, inductor, and capacitor. And it is not applicable for unilateral elements, means diode, semiconductors, and transistors. So these are the limitations of Ohm's law. Limitations of Ohm's law. Relation of circuit elements. Relation of circuit elements. So this part I will cover in the next video. Thank you. Next, in the next video, I will cover relation of circuit elements. So till now we discussed about electrostatics, magnetostatics, and time varying magnetic fields. So according to Faraday's law, if one quantity is stationary, another quantity should be varying with respect to time or space. Then only you will get some result. After that we discussed about Ohm's law. So applied means current is directly proportional to applied voltage. So this is about first session. In the next session we will discuss about relation of circuit elements, that is RLC properties and units. Thank you.